You can also use your own sample data. Uh, for beginning, we will just try to do with known data so that you don't have face any problems. Later on, you can try on your own samples because tomorrow you will. I will send you the quiz, two quiz and assignments. So these assignments you can practice, and then you have to uh, send it back to me. Okay, so you can upload in the Google form. So then we will see, like, if you have any problem, then I can answer the queries if you have any queries. So this is how we will do it. So today I will explain the concepts uh, one by one. Then you practice in yourself, and if you have any problem, you send an email or something. So tomorrow, most of the day you can practice, or even today afternoon you can practice. So we will send the assignment and everything in the afternoon. Okay, by afternoon we will send it. So after this session, I will try to send you the all the assignment and also your quiz. Okay. So yesterday we learned some few things about how to use this foolproof. Just it was just to beginning, just to get you the idea, and also just if you are the first time user, then it would be easy for you to see or to get more familiar with the icons and all this. Okay, so today, first session, we are going to do phase matching. So why you need a phase matching is the main thing is for instance, if you are so I gave an example of TaO2. The TaO2, you may be looking for anatase, or you may be looking for rutile, depending on what kind of application you want to do. So in that case, what happens? You may not exactly if you are going for higher temperature, then your anatase would be mostly changing to rutile, or it may be in some mixed phase. Okay, so in your case, you may be looking only for pure anatase. So in that case, only way to, or the more appropriate way is to do the phase analysis. Okay, so phase analysis will give the basic information about whether you're having a pure phase or you are having some impurity. Okay, so in this case, you have three X-ray diffraction here. So the bottom one is a pure anatase phase. The up one is purely rutile phase. The one in the middle is a mix of both anatase and rutile. So these things you need to know before you start your any other further analysis. Okay, or even before starting your main applications. So you may have to know this. That is the reason that why we are going to do phase identification. And also you'll get, when you do the phase identification, you get the basic information like your space group and also your lattice parameter. So this, with this idea, you can go further for profile matching and retool refinement. So that is, this will be your starting point. So that is the main reason why we are going to do this phase matching. So the first thing when you get your X-ray diffraction is, so you check your data, and then you first thing you do is your phase match. Okay. Then after that you can go for the further analysis, profile matching or profile fitting and also. Okay. So this is your approach. First you check the uh, your quality of data, then you go for determination of peaks and profiles. Okay, so now what I will do is I'll just go directly to the phase analysis, to this part, and then we'll start here. Okay, so why you need the phase analysis? So if you see some papers, what they normally do is they will just take some data, JCPDS data. So JCPDS and ICDD are both are the same. Okay, so this we already discussed in the previous one. So I think yes, here. So they may give some JCPDF number. This means this the number which is given refers to a particular compound or a particular entry. Sometimes what happens for the same compound there may be multiple entries. Like for TiO2 anatase, there may be one for bulk anatase, one for nano anatase. So they keep adding the data on in this database, and they call this as either JCPDS or ICDD or ICSD. So these are standard databases. So previously it was called JCPDS. Now they have changed it to ICDD. So both are same. So they give that number. That number refers to some particular record in that database. So you don't have to always give that information because as I told, even for the same compound, there may be multiple entries. So when you give that number, that means okay, you have gone through some database, but it doesn't mean that you are having a very pure face. Okay, so this is what they normally do. JCPD some number they give. So this refers to some compound, and then you get some lines here. Okay, but uh, here I am asking this question: is this profile match correct? So we will come back to this again the same slide after we learn what is profile matching. Okay. So right now, if I tell it may not be proper. So what we will do is we will first try to go for analysis, or I will explain the concept. Then we will come back to the same slide. Okay. So now, if you take any sample, once you get this spectra, it is always important to do something what we call as the position, and you to do the intensity. Okay. So for example, if I have some SiO2, so I'm taking a SiO2, it may be a nanoparticle or nano powder. If I do XRD, I'll get some lines. Okay. So this is not a spectra, it is just a representation that, okay, so if you will peak in this position. Okay. So this means there is a peak here in this position, and then there is a second peak at some other position. So your x-axis is normally 2 theta, and y-axis is your intensity. Okay. So first thing what you do is you have to see the peak position and the intensity. So next, what I have done is I have done X-ray diffraction for NaCl. So this is having some peaks like this. Okay. So I have given two different colors just to show. Okay, these are two different samples. Okay. So now if I just mix means I'll just take some 0.5 grams of SiO2 and maybe 0.25 or zero point 0.5 grams of NaCl. I'll just grind it or just mix it by spoon. Okay, and then I will take the X-ray of that mixed powder. So normally what you get is you get these kind of lines. So how to interpret this is you should interpret with respect to the your starting samples. Okay, so I have taken SiO2, I have taken NaCl. So if I am trying to make a new compound, maybe like a sodium silicon oxide or something like that, so then what happens? I should get a different spectrum if it is they are reacting. If they are not reacting, then what happens? You get some peaks. You get the peaks from both SiO2 and NaCl. Okay. So if you see here, if you take this black one, it is just a combination of your blue lines and red lines. So there is one line here. So this corresponds to this line. There is a shorter line here. This corresponds to this line. This line is for this line. Okay. And then this is correspond to same line. Okay. So this is just like mixing two. If I put both of them together, then what happens? I get this. So I will show you more accurately. Okay. So if I just keep it like this, then what happens is you get the black one. Okay. So if you see now, uh, so if you see the black one is just it's just combination of your blue and the red. Okay. So blue is your SiO2 and red is your NaCl. So now if you want to know what are the combination, then you have to do something called as a phase match. So what this phase match does is it will we use some, you can use any softwares. So normally we are using QualX, but you can also use some commercial softwares like iScore Plus from your Panadical, or Brooker. They have Topaz and Eva. So you can use any of them, but if you want to use them, then it should be you need to pay for that. So that is the only reason why I'm picking the QualX. Okay, but the concept will be same whether you're using QualX, whether you're using Profex or Eva or iScore, doesn't matter. The concept is same. So I'm trying to I will explain the concept. You can choose your own choice of software. So that is not I cannot impose that you have to use only this one, because every software has its own advantage and disadvantage. Okay. So now if I take, as I told, this is a combination of both. Then what? How do you know what is which one? Then you have to just to see, okay, so this peak is coming from NaCl. So these two peaks are coming from NaCl, and if you go for some of the peaks like this is come from SiO2, okay, silicon oxide. So this is one thing. Then the intensity actually depends on the concentration of the your phase. Okay, so I will call this is your SiO2 phase, and this I will call this as a NaCl phase. So now if I mix both in similar ratio, then I may get just same intensity. Okay, but if I take very small amount of NaCl, maybe like I will take some I will take 1 gram of SiO2, and if I take 0.1 gram of NaCl, then what happens? Instead of getting these high peaks, these peaks would be the height of the peaks would be smaller compared to the previous one. Okay, so if I reverse it, like if I take 1 gram of NaCl and if I take 0.1 gram of SiO2, then what happens? So these peaks which are corresponding to SiO2 will become smaller, and the other peaks will become bigger. Okay, so this intensity actually corresponds to the amount of phase which is present in the sample. Okay, so that is why both intensity and position would be very important in doing your X-ray diffraction analysis. So now I will, this is a combination. So now I will give one more example. Like this is the same thing. So I have SiO2 in blue. I have NaCl in red. So now can I say this is just the combination of an SiO2 and NaCl? So in that case, you have to check each peaks. Okay, so first peak is fine because it is having some intensity. Then this blue is somewhere here. So it is, if I say it is fine, then okay. Then if I take this blue, this is there, and then this blue is there. And now the intensity is matching. Okay, so if I this is if I take this is 100%, this may be 75, and this may be 50. So 100, 75, 50. It is just some average. Okay, but when it comes to NaCl, if you see the peaks for NaCl, this is shorter. This is the highest peak. So if I call, if I consider this is like 100%, then this is around 75, this is around 70, and this may be around 30, 40. Okay. But if I take the same position peak here, what happens here is, so in this case, so this peak is shorter, but the one this peak is having more intensity. So now there is a mismatch in intensity. So this I cannot tell, okay, this is a mixture of NaCl and SiO2. Okay, because even both the intensity ratios and the peak position should match. Okay, so in this case, what happened? The intensity ratio is same. So this is 100%. Then this is maybe 75, and then this is 70. Uh, so now if I take the other one, so like if I take in this case, so this is 100, then this is maybe 75, and then this is 70. So they have the similar uh, intensity ratio. Okay, but if in this case you don't have the same intensity ratio, so this cannot, in this case I cannot tell it is a mixture of NaCl and SiO2. So these are things that you have to take care when you do the phase matching. Okay, the position and also your the peak position and also the intensity ratio should be almost same. Okay, So this is just one example where I wanted to give more explanation on the on your phase identification. So now I will go to next one. So in some case, what happens in the previous one, what I did is I just took SiO2, I took NaCl, I mixed it by spoon or grind it by mortar pestle. Then I took the X-ray diffraction. So that gives some spectrum. In the second case, what we do is I will take cerium oxide. So, okay, I think so. I will take a cerium oxide and then I will take zirconium oxide, CuO2, and also uh, so this first one is the cerium oxide, and then what I will do, I will take a zirconium oxide. So CO2 and the ZrO2 both are in almost similar oxidation state. Then what I do is I just grind it, and or I just mix it with using a mortar pestle, and I sinter it at high temperature. Okay, if I do that, then what happens is uh, there may be reaction between your cerium oxide and the zirconium oxide. Okay, so let us assume in this case what they have done is they have taken cerium oxide and they have put a very small amount, maybe 0.1 0.2% of zirconium oxide, and they have done this experiment. So now what happens in this case is, so So in this case, what is happening? Instead of getting two separate peaks, I'm getting only one phase. Okay. So the reason is your zirconium is going into the lattice of cerium oxide. Okay. So that means if I'm taking some zirconium oxide, then what happens? This zirconium oxide is replaced by sorry, your cerium oxide is replaced by zirconium oxide. So in that case, you may not get two different patterns. Instead, you get only single pattern. Okay. So this is a nanoparticle. So in that case, you get wider your more wide peaks. Okay. So instead, if it is a bulk, then it will become a very sharp peak. So now here, if you see this peak intensity is same. The second peak is slightly lesser, and then there is some peak here. Okay, so only thing is the position of the peak is changing. This means you're having some reaction of cerium with zirconia. Okay, so now why it is shifting to the right is, so if you see the cerium oxide at your size is 2.7 angstroms, and then if you see the size of your zirconia would be slightly lesser. Okay, so in that case your zirconia would be more 2.16. Okay, so your cerium is 2.7. So in this case, what happens? You are trying to put a smaller particle into in place of a bigger particle. So your lattice parameter or your the unit cell would shrink. So the unit cell shrinks means your if you use your n lambda is equal to 2d sine theta. So I will just so if you use n lambda is equal to 2d sine theta. So in your case, theta is constant. It is the same. Lambda is same, n is same. So when you are changing your when you're changing, d is actually the interplanar spacing. Okay, so this is your interplanar spacing d. So if I am putting a smaller particle, then what happens? This distance has to decrease. Okay, so it is shrinking. So if your d is decreasing, d is inversely proportional to your theta. So d is equal to your n lambda by 2 sine theta. So in that case, what happens? Your theta is actually increasing. Okay, so or if I put sine theta is equal to n lambda by d, then your theta is going to increase. So that is why it is going to shift to the right. Okay, so these peaks are shifting to the right. So from here to here, it is shifting to the right. If I, instead of this, if I do the reverse order, like if I take a zirconium, which is a smaller particle, So if I take zirconia, which is a smaller particle, and if I try to put cerium inside that, then what happens? This trend has to reverse. That means your peak has to go to the uh, left side. Okay. So that means you're increasing the D. So as you're increasing the D, then in that case, what would happen? Your theta would decrease. So the peak position should shift to the left. Okay. So but there is some things that you need to keep in mind. This kind of shifting is not you cannot just tell, okay, there is a shift in peak, so I have doping. Okay. So sometimes what happens, even if you have some uh, sample preparation, if you don't do a sample preparation properly, then also you can have this kind of shift. Okay. So if you fill your if you have some sample loader, something like this is the cavity of your sample loader, and if I put some sample below this reference point. Okay. And if I take the data, then I get peak position here, somewhere here. Okay. And if I put exactly uh, to the reference point, then there may be the same peak may shift to different position. Okay. And if I give put more sample, like if I put more sample which is above your reference line, then again it will shift to right side or left side. Okay. So this you need to take care. So when you prepare your sample for X-ray diffraction, always try to take your sample holder. So it may have some 1 mm or some depth. So always try to fill exactly to the height of this sample your the reference line. Okay. If you put more or less, then again you can have, there is a possibility you have to have this kind of shift. Okay. So these things you need to take care when you prepare the sample for uh, X-ray diffraction. So other than that, if you're maintaining this kind of sample height, like if you're having a constant sample height for all the samples, and you're trying to dope something, then and still you can see this kind of trend that your peaks is shifting. That means this refers to the doping. Okay, so the zirconium is going into the cerium side. Okay. So now there is one more precaution that you need to take. So if you take a polycrystalline sample and if you do powder diffraction, you get peaks like something like this. Okay. But if you are working on a single crystal and if you try to do powder diffraction, okay. So instead of single crystal diffraction, you should be
काय
careful because
हा अरे देतो ना एवढ्याशा गोष्टीसाठी का
okay. So if you're trying to take a X-ray diffraction of single crystal data on a powder diffraction on a powder diffractometer, then what happens is you may lose some intensity. Okay, because in case of your polycrystalline, so there are three things. One is amorphous. So what is the meaning of amorphous? Amorphous means there is no arrangement. If I take amorphous material, then what happens, the atoms are scattered randomly. Okay. So for in case of a polycrystalline, what happens, or if you take a single crystal, then what happens, your atoms are regularly arranged, so they are next to each other, so they form some regular pattern. Okay, something like this. And if you take a polycrystalline, in the polycrystalline sample, what happens, there is ordering but micro ordering. That means there is sample or the atoms are arranged in this small crystal, and then there may be one more crystal which is having a different orientation. Okay, so there is polycrystal is nothing but it is a many single crystals. Okay, so poly means many small single crystal will become a polycrystalline. Okay, so in case of a polycrystalline sample, what happens is you can have grains which are having different orientation. Okay, so this it is shown here. So this blue is oriented in one direction. So this may corresponds to, this will give something like 100 direction. Okay, or 100 reflection. There may be some other which is tilted in a different way. So in this case, what happen, you get you will satisfy the Bragg's law uh, for 110. Okay, in the first case you satisfy the Bragg's law for 100 at around 20 point something. Okay, 2 theta. And when you come to close to 30, you may satisfy the Bragg's law for 110. Okay, and similarly with as your X-ray and your detector is moving, so this is your angle of incidence. Okay, so then in that case what happens is, as you move, keep on moving, at some angle you are going to satisfy Bragg's law, so you get constructive interference, so you get a peak here. Okay, but in case in other places there may not be uh, so there may not be some kind of, or in the in between the two peaks, what happens is you may not satisfy any Bragg's law, so you won't get any diffraction, constructive interference. So there is, if there is no constructive interference, then you don't get any peaks here. Okay, so this is how you get different peaks in a given X-ray diffraction pattern. But if you take the same single crystal, what happens? You have only one orientation. Okay, it may be either oriented in 100 or 110. Okay, so in that case what happens, you get peaks only corresponding to that orientation. So if you take the next orientation, like for example in this case you are getting orientation for 100, so you get peaks for 100, 200, and so on. Okay, but you may not get the peaks for 110. So here you can see there is a peak here for 110, but on a single crystal data, you, like if you take a single crystal and do a powder diffraction, you may not get those peaks. Okay, so these things you need to take care. And even you can see 111, as there is some contribution from 100 plane, so you may see small peaks, but this intensity is not same. Okay, so that is the reason, if you want to do a single crystal X-ray diffraction on a powder diffractometer, you need to grind it very well. That means you take a big crystal, you make it a lot of small crystals. Okay, so that is the meaning of your polycrystalline. But you should be very careful. In some cases, what happens, your crystal may lose its property. Like it can change its phase and it can change its property when you put some mechanical stress. So when I try to break it into small pieces, it may change, especially if you are working on shape memory alloys. So in that case, what happens? If you put some stress, then the phase and the symmetry of the crystal will change. So, but in most of the cases, it doesn't happen. Only in some cases, those things would happen. Okay. So these are some of the things which you need to keep in your mind when you are working on a single crystal and taking and trying to do powder diffraction data. Okay. So next, so what we'll do now is we will just take some example and I will show how to get or how to do a phase identification. Okay. So what I think, okay. So for this we are going to use our QualX. So we use QualX. The procedure whatever we follow here is same for all the softwares. Whether you're using QualX or EVA or iScore or Profex, whatever software you use for identification, it is the same procedure. The first step is you have to identify the peak position and you should identify the peak intensity. Okay, so as I explained in case of SiO2 and NaCl, so you need to take care of the peak position and also peak intensity. So based on that, you can identify whether your sample is in which phase. Okay, so that is the one thing you need to keep in mind. So now what I will do is we will open this QualX. So in this QualX, what I will try to do initially, I will just do simple ones. Okay, so you can go open your QualX, check if you have your database. So once you put the database, it will stay there. Okay, you don't have to again put the database. Only in the starting, in the first case, you need, or when you're using this for first time, you need to give link. Okay, so I'll just show if someone has missed it. Okay, I will delete it. So let us assume I have just uh, I have installed the QualX for the first time. Okay, if I have installed the QualX for first time, then what happens? I open my QualX, and if I go to the search and if I go to database, that means I need to link a database. Okay, So if I go here, I can see there's no database which is present here. So now first step, what I do is I have to uh, link the database. So for this, I will click here on the new, and then so I have saved my database on the desktop. Okay, so QWCOD, I have extracted here all the data. So I have to just select this .sq. Okay, I'm going to select the sq and I am going to open it. So now, right now, what it shows, it is showing, it is showing this database is not selected. So what you normally do, you just click on this line and you click the select of QWCOD. Okay, so then you can close it. So now if you go back, you see there is this database is selected. Okay, so this means this has been you have already taken the database now, right now. Okay, so now what we will do is we will our system is, or our software is ready to do the uh, face identification. Okay, so I request all of you to please mute, because sometimes it will be uh, there will be two echoes sometimes. Okay, so now you need to, first thing is you need to import the data. So I have sent some data files in the morning for your in your to your emails. So you can download those data and you can work. Okay, so initially what I will do is I'll just take the example which is in foolproof suite. Okay, so foolproof suite, if you go to examples, then there are so many uh, so many examples already, data extracted data. I can use those things. Okay, so one thing what you need to take care is this QualX cannot open all the database, sorry, all the data. You should always for simplicity just keep it as xy. Okay, you convert it into xy. So this is the reason I showed you to how to convert the sample. Okay, I will again show it again. Okay, so you take your data from whatever machine it is coming, and then you try to uh, you can try to convert it into xy form. Okay, so this can read all this xy form and all these things, but try for simplicity is better to have xy. Okay, I'm going to open this. Then it will ask what kind of x-rays did you use. Okay, so in this case I know this is the copper radiation. If you have used cobalt radiation, you can click cobalt. If you have used molybdenum, you can use molybdenum. If you have used silver, then you can use silver. Okay, but I know this I have used copper radiation, so I'm going to select this copper radiation. Okay, so now you can see this is having some peaks. Okay, so now I want to do the phase identification. So first, before doing phase identification, you need to try to do the background correction, or you have to take the background and you have to take the peaks. The reason why you need to take the background is the intensity always may not start from zero. Okay, for example, in this case, this count is already having some two counts. Okay, so this is having two counts. Okay, and then in some cases, if you have high fluorescent sample, like your iron, the sample with some iron and all those things, then what happens? This intensity is going to increase. It may be in hundreds, or sometimes in, even it can go to 200, 300 intensity. Okay, so in that case, you don't know whether the what is the exact intensity of each piece. Okay, so that is the main reason why we have to select the background. Okay, so for this, what you do is you can if you want to unzoom, you have to click this resize, then you will get complete spectrum. So in this case, you can see it, this data is having up to more than 142 data. Okay, so if I want to zoom, what I do is I just click here, and you don't remove the your finger. Okay, so you click on the left button on your mouse, and then you drag it and then leave it. So whatever you select, those things will be zoomed. Okay, so you can zoom those portion. Now what I do, I go for pattern again, and I can do the background option. There are two kinds of background option. One is, so if I click this background option, you get one more window, so where you can see it has already put some points. Okay, so if this is already having some points, so just a minute, I will stop sharing because there is some echo. So I will try to change the settings. Hello, can you hear me? Okay, okay. So we will continue. So now what you do is you just uh, try to select the background point. So in this case, you can see already it has put some line points here. The things which are in the red. Okay, and there is a green line which would actually connect all these points. So what you need to check is when it is doing automatic, you should check whether it is putting so it is trying to put some points here. You should take care like these points are not in the middle. Okay, so how to remove or how to add, you can use this button here, and you can try to add here. So if I want to add some point here, I'll just click here by using if I activate this. Okay, so there is a button here which should take care of those things. Okay, so now if I want to remove the points, so for example, if I want to remove the points which is in middle of some points, then what I do is I will zoom is, then I want to remove this. So what I will do, I will go to the same background options, and I click this. If I click on the left button, it is going to put a it is going to add some points. If I click right button, okay, so right mouse button, then it is going to remove the points. Okay, so these things you need to know. So left is going to insert the points, and the right button is going to remove the points. Okay, so you just go close to the point which you want to remove. So if I want to remove this point, I go close to this, and then I right click this. Okay, so this is how you can add and remove your own points. Okay, so you can change these things, and then once you are satisfied, like if you think all the points are fine, then you can press OK. Okay, so now you can see it has already put the background points. Next step is you need to select the peaks. Okay, so for this what I do is I'm going to go for search peaks. So initially I went to background options. Now I'm going to go for peak search options. Okay, so now if I see this, then what happens, you can see it has right now it has put some peaks here. Okay, and if I want to remove or add, then what I can do, I can actually use this threshold or sensitivity. So if I do this if I change these bars, you can see it is putting some peaks, or it is just removing some peaks. Okay, so these things you can do, or if you want to again add manually, you can click this button, and if you want to add some peaks over here, then what you do, just go and click on the left mouse. Okay, and if I want to remove the peaks, okay, so what I do the same thing. So I go to peaks option, and then take this and I click right button. So if I click right button, it is going to remove the peaks. Okay. So I want to remove this, then I go close this, then just click a right button. Okay. So this is how you can do the selection of peaks. Okay. So now once you have chosen all the peaks, so in this case I have chosen all the peaks. So maybe there is one small peak which is missing here. I will try to take that. I will add this peak, and then now what happens is you can we can go for search match. Okay, what is the meaning of search match? Is search match is it will try to find the position and intensity and try to search some material which is already reported. Okay, so you go to search, and then you can do two ways. One, you can just blindly do search match. The second one is you can do your restrain is nothing but when you know what are the materials which are present, or when you know what are the elements which are present, you can use these constraints. Okay, so sometimes what happens if you have too many peaks, then your software may not be able to uh, detect the all the uh, proper elements. Okay, so it is better if you know the elements which are in the sample. So for example, this is a CO2 sample. So I know there is cerium and there is oxygen. So I can put cerium and oxygen. Then I can ask the software to search only for the elements which are or the data files which are having cerium and oxygen, instead of looking for all the elements. Okay, so this is this is one way to reduce the time and also to get more precise information. Okay, so there are other possibilities, like you can also give some sub files, whether it is organic, inorganic. Okay, you can also type your chemical names, like this is a cerium oxide, so I can put cerium oxide. And if I know the symmetry, I can take the symmetry. So but anyhow, if you don't know anything, just put the elements which are present in your sample. Okay, so I have cerium and oxygen, then I can use cerium and oxygen, or you can also use different uh, boolean or different conditions. Okay, and or not, so these things you can use. But normally if it is only two, then I am just using cerium and oxygen. Okay, then I can what I do is I will just do search with these constraints. Okay, that means look for the database with only these two elements. Okay, so I'm going, if I do this search with constraint, then what happens, it will give some possibilities. Okay, so it is giving some possibility, like here cerium oxide, then some dy doped cerium oxide. Okay, so gadolinium doped cerium oxide, so all the possibility it is going to give. So you can now choose which is the exact or which is a good match. Okay, so normally if there is a very small doping, so you may not have you will not have a completely new pattern. Instead, you'll have only shift in the peak position. Okay, so this is the same thing which I showed in case of your cerium oxide dope with zirconia. Okay, when you dope with zirconia, only the peak position is going to shift. You may not get any new peaks. Okay, instead of that, if there is no reaction, that means if you have taken cerium oxide and zirconium oxide, you have tried to do the reaction at very low temperature. That means zirconium is not going into the structure, but it is just staying as zirconium. So in that case, what happens, you'll find new peaks. Okay, there will be some different peaks, that also we will see in the next examples. Okay, one or two examples. So those things you need to take care. Okay, so now you can, in this case, what you do is, if you go here, you need to first see the peak position. So this is already here. Okay, so if you see the first two rows, sorry, first two columns are for your sample. Okay, once you do your peak search, then what it will do, it will put the 2 theta and the corresponding intensity. Okay, so for example, this peak is having the peak position is, so you can go close to this peak and you can watch this column. Okay, if you see this row, then you can see it will give the peak position. Okay, So 2 theta is around 2.43 and count is around 961. Okay. So what it has done is it has just rounded it off to 1000. So 2.58 is the position, and then the intensity is 1000. So next peak, if I come here, so this is around 33.06. So it is put 33.1, and then it has put the intensity. So these two, this first two, it corresponds to your sample. Okay, whatever sample you are taking, then you are getting a new two more columns. These columns corresponds to the selected database. Okay, so if I select this, then it will take the data from here. If I select something here, then it will take the data from that. Okay, so you can see here it is changing here. So this is yttrium doped cerium oxide. So if I click here, it is just a cerium oxide. Okay, cerianite. Okay, so this is how you can select these things. And what you are supposed to do is you have to see whether it is taking all the peaks. So in this case, it's a very simple example. So if I just zoom this portion, only the bottom one, the red one is correspond to the peak position from your sample, okay, from your data. And the next very light green one, so this corresponds to the peak from your database. So it is exactly matching, and also you can see the intensity is matching. Okay, so first peak is around 1000, this is also close to 1000. Next peak is 270, 270, 294. Okay, and then if you take the third one, it is 491, and here it is 481, and this is 400 and 396. There is small difference, but this difference is fine. But if you're instead of this, like if you're having this is 1000, this is 1000, and this is 270, and this is 750, then it is not a good match. Okay, so these are very close to each other, so you can consider this is the perfect match. Okay, or this is one of the phase. So once you want to just select, what you do is you can click on this, or you can click on this tick mark. Okay, that means I'm going to accept this. So if I accept this, then what it will do, it will give the other options. But as I know, it is taking all the peaks except some peaks. So if you want to see what is this peak, so this is around 69, so 69.4 to 69. So there is some small shift, but it's okay. Like, it is already taken. Okay, so sometimes it may not give the exact peak position, but it is fine. It has taken most of the peaks. So this now you can say your data is for your CO2 sample. Okay, so if I want to know what are the phases, then what you do, you just click on this line, and there is something called as show card. Okay, so you click on this show card option, then you will get the information about that all the peaks. Okay, and also the symmetry. So you can see here this cerium oxide is having Fm minus 3m. It crystallizes in Fm minus 3m space group, and the lattice parameter is 5.411. Okay, and then it is also giving the peak position and with intensity. Okay, and also you can see there is something called as HKL. So these are the Miller indices corresponding to your each peak. So the first peak is 111 peak, the second peak is 200 peak. Okay, then third peak is 220. So this is how you can also get some preliminary information about the HKL or the Miller indices of your sample. Okay, so this is how you do the phase match. So if you have any doubt, I will take the question, then I will go for the uh, next one.
Sir, can you repeat this one, sir? One more time.
Which one?
There is a card in about this one.
Okay, fine.
Please.
So I'll just answer this some questions, then I will come back. Okay. So audio, is it fine
Sure, sir.
now?
Yes, it's fine, sir.
Okay. So there is not all peaks in the case of zirconia do shifted to the right number. So okay. So in this case, I think all the peaks are shifting, because see, if you take this midpoint, this is shifting here, even if I take this point, this is shifting here. So even this is the midpoint. You have to take the midpoint. So when you take the midpoint, then you can see it is clearly shifting. Yes, in some cases there may not shift all the time. Okay, so all in all cases it may not shift. Okay, so again it depends on the lattice. Okay, so when you are having ABC, your ABC depends on your unit cell. Okay, right? So when you have, for example, if this is your tetragonal system, so in that case, what happens? You are having this kind of A, where A is equal to B, but it is not equal to C. That means this is your C axis. Okay, so you're having, this is your A axis. So for example, if your atom is changing only your A axis, okay. So in that case, what happens? That means if it is changing only the your A parameter, if it is not changing the C parameter, so in that case, what happens? The peaks which are corresponding to AB, they're like 110 or 100 or 010 will shift. Okay. If it is not affecting the C axis, that means the peak position for C would remain same. Okay, that means you're not changing the your uh, uh, C parameter. That means all the entire shape may not be changing, or it is not shrinking in all the shapes. Okay, so these are very special cases, not in all the cases. So most of the times once you dope something, then what happens? It will try to change the entire unit cell. Okay, so that is how you have shrinking of your unit cell. The volume is going to change or something like that. Okay, okay. So I'll just so instead of JCPDF card or for particular compound, can we use COD card? So normally COD is not COD means it is a crystallographic open database. Okay, open database, it is not actually identified by your crystallography community as a authentic. Okay, so normally what happens? COD, even you can put your own database. Okay, you can anyone from anywhere from the world, they can create their own COD and they can add it. Okay, so normally this is not authenticated. JCPDF is normally authenticated, means it is been tested by some experts and then it was done. Okay, so JCPDF is now it is ICDD, so you can put those cards, but it once you're if you're doing your profile matching and those things, then you don't have to give your JCPDF card, because you are already giving your own refined A parameter, B parameter, C parameter, and symmetry. So in that case, it is not like mandatory to give the JCPDS. So in some case, for example, in this case, what they have done is they have just given their data and then they have just shown, okay, this is matching with some JCPDS data. Okay, but when you're doing profile matching, you will see that you're going to try to fit your data with the model. Model is with your space group and ABC. So in that case, you can just view, okay, these are the refined parameters. So that is almost like authenticated. Okay, so that in that case, you don't have to always go for JCPDS data. So then, okay, so when you have zoomed in a XRD data around 70 degree, it has two peaks. However, the table has one peak. Okay, fine. So this the second peak, as I explained in the previous yesterday also. So if you take any higher angle, okay, so anything above your 60, if you start seeing, like you can see that each peak is into two peaks. Okay, this peak is mainly because first peak is coming from K alpha 1, the second peak is coming from K alpha 2. Okay, so this is the same peak. The meaning is like this is around 69. So 69, if I go here, so 69 point something, it gives a 400 reflection. Okay, so both are 400 reflection, but as you are having two different wavelengths, like K alpha and K alpha 2, you will see both two peaks, okay, instead of one peak. So this is more prominent at higher angles. So even if you go to much higher angle, you can see here these two peaks are well defined. Okay, so this is mainly because this is this will have some scattering at a higher angle. So this again I will explain in the later stage. Okay, so why you have this kind of peaks. Okay, and if you are using monochromator, like if you are using only copper K alpha, then what happens? You will never see this second peak. You have only one peak. In all the place, you will have only one peak. So I will show that example also. So and this peak at low angles, it will be almost close. So there are two peaks, but it is still showing as almost one peak with some shoulder. Okay, so this is from K alpha 1, this is from K alpha 2. So if you go for much lower, then you may not even notice the K alpha 1. Okay, so they are almost merging. So in this case, you can see this is almost merging in the both are merging. Okay, so that is the reason why you are not seeing that. Okay, okay. So now I will ask you whether this is a good fit or whether this is a good profile matching. Okay, so you can see here in this, if they are giving, this is your JCPDF data, which is from your database. They are saying, okay, this is matching with. Okay, I think I'll make it big so that. So they are claiming that their sample is actually matching your this database. Okay, but if you look carefully, so you can see this peak is there. Okay, this is good, but here there are two peaks and they see one peak and one small peak. Okay, we'll consider this is a peak and this is a next peak. And if you go for the main peak, there are actually three peaks instead of two peaks. Okay, if you see very carefully, you can see there is a three peaks. Okay, we can ignore this, maybe some due to some other radiation. In that case, what happens? There are two peaks. Okay, this is two peaks, but here when you go for the higher angle, you can see here there is one, two, three peaks, but you have only one peak. So in this case, what happens is this is not a proper profile match. Okay, so you need to consider all the peaks. In this case, what does it mean is there may be second phase. Okay, or there may be some impurity in this sample. And if even if you go to higher angles, so even at higher angles, so even at higher angles, you can see this intensity is not the same as in case of your in case of this JCPDS data. Okay, so these things you need to take care. So even if you see here, there is a lot of intensity mismatch. Okay, so this peak is having more intensity, but here almost all the peaks are having the same intensity. So this means this is not really good profile match. Okay, so this is one thing, one example which you need to take care. Okay, so when you do this kind of profile matching. Okay, so why this profile matching is important is this will serve as a basic model, or this will serve as a model for doing further analysis, your profile matching or ritual refinement. Okay, so if you don't do your profile matching properly, then it doesn't make any sense if you do a good ritual refinement or something, right? Okay, so okay, I will just come back to this. While selecting data background points, what should be an ideal chi-square value in QualX? I think, see, here we are not doing any kind of what to say. We are not doing any quantitative analysis. Okay, so your chi-square is more important when you're doing a quantitative analysis. So anything, yes, the close to one is good. Okay, so if you take your scale here, in this case, this close to one, so this is good. Okay, so even if you see this yes quantitative, you can see. So anything very close to one is fine, no problem. Okay, so this is very basic information that you're trying to get. So in that case, you don't worry too much about chi-square here. But this chi-square, you need to worry when you're doing a profile match or ritual refinement. Okay, so if this is more like you see what are the things you are having here. Okay, your peak position is matching with both your data and database, and your intensity is having good agreement, like it is having the same change. Okay, so this is like percentage. Okay, so if you're having that kind of agreement, then you don't have to worry too much about the chi-square and all, because this is just starting one. Okay, later you are going to use this information and do more qualitative and quantitative analysis. Okay, so this is fine. If anything with which is very close to one, with this scale is a good agreement. Okay. Oh, so in the card information, D stands for. Yes, so this D stands for your D spacing. D spacing for 111 plane. Okay, so if I take the first D spacing, so this corresponds to 111 plane. And then if I take the second D spacing, this corresponds to 200 plane. Okay, so D200, this is what I explained in the last session. So if you take two different, even if you take any crystals, they will have different planes, crystallographic planes. So if I want to, I will just give very good example here. So thanks for asking. So Reshma, so thank you very much. It's very good question. Reason is, see, this D is linked with your parameter. How it is linked with parameter? So I will take, this is a cubic system. Cubic system is A is equal to B is equal to C. So now if I take this cubic system, this is corresponds to D200. That means it is your plane 200 plane. So normally if I want to have your I think I'll take some example. Okay, okay, so this is your, if I take, this is my unit cell. Okay, and if I take this is my x-axis. I'm not good in drawing here, so sorry for that. So if this is your x-axis, then this would become your, if I take, this is my origin, and then this is my A parameter, then this would become your 100 plane. Okay, so then 200 plane would be somewhere in the middle, exactly in the middle. You will have this plane. If I take this plane, which is in the center, this is actually your 200 plane. Okay, for a cubic system. So now if I come back to this your QualX, okay, so I'll just come back to QualX. I will just see here 200 plane is having value of 2.055. Okay, so uh, so D200 is having value of 2.7055. This means it is half of your A, right? So if I take from here to A, this is your A parameter. It is just half of your A. That means I'm just taking this value. This is your 200, D200. D200 is 2.75. So if I multiply by 2 times, then what happens? It will be something like 5.410 something. Okay. So if you check your A parameter for this particular example, if you see here, A is 2.544. So, sorry, 5411. So this is how you can have link between your D spacing and space group. Okay. So A is 2 times of this, so you get to 2.411. So this is the exact thing what you have for your A parameter. Okay. So this is how you this D refers to the spacing for that particular plane. So next is for 220 like this. Okay. So this is one way you can also clarify whether you are having a proper D parameter D correspond to that particular plane. Okay. And if you go for 400, then it will be almost 4 times. Okay. So you just multiply this by 4 times, then you will get your A parameter. Okay. So this is one way to do it, and you can use this. But here what happens? You have to multiply by instead of 2, you have to multiply by 2 root 2. If I multiply this with 2 root 2, then I would get this again A parameter, same values. Okay. So this is how you can actually get your parameter. Okay. So explain multiplicity. Multiplicity we will come back, because right now we don't worry too much. When we do the ritual refinement, when we go for ritual refinement, I will explain this about the multiplicity. Okay, so let us not load too many things, because if someone is for first time, then it will be very much difficult to grasp all the things. Okay, so I will keep this multiplicity for Monday or Monday session. Okay, when we do ritual refinement, we are going to talk about that. Okay, so if nothing is there, then what I will do is I will just repeat this again. So what I will do, I will just go for new. Okay, then I will just start again. Okay, so if I go here, I will first thing is I will check my database. I have my database as I'm already using it. So then what I will do is I will go for file. I will import the file. So let me import the same serium oxide, or let us go for next one. Okay, maybe we will take simple one. I will take lead sulfate. Okay, PbSO4. Okay, I think it is not. Okay, we'll see what is okay. PbSOX. Okay, so PbSOX. So you can see this is having more peaks. So and this is done in copper radiation. So I'll tell okay. Now what you do is you don't have to do when you want to do profile matching. You don't have to do for all the angles. Okay, you don't have to do from 10 to 60. Even if you do for the, if you have something like 10 15 peaks already, that is already sufficient. Okay, so I'll choose only this one. I'm going to zoom this part, and we will do only we will do the profile matching only for this portion. So that would be already repeated in the next part also. Okay, so if you have anything more than 6 peaks, that is already good. Here we are already having more than 10 peaks, so this pattern is sufficient. Okay, so now first thing what you do is you go for background options. So pattern background option, if you want you can zoom it, and you can see. So if there is any peaks which is in the middle of some peak, you can remove. Or so I want to remove this, what I will do is I'll click this, and I'm going to click right button, so it will remove the points. Okay, so right now I think it is fine. There's not much difference. So let us take as it is. Then what I do is I'll go again for peak search. I have to search what is the position of the peak. So I'm going to do this peak search, and you need to be very careful, especially if there is some doublet, like in this case. You can see this is again from K alpha 1 and alpha 2, alpha 1 and alpha 2. So sometimes it may take both the peaks. Sometimes it may not take the peaks, both the peaks. Okay. So, but you should, if you know which peak is from K alpha 1 and K alpha 2, then it's fine. You can take care of that in the later part. Okay. So if you want, you can play with this. So you can see when it is in low, there is a lot of peaks here, which may not exactly correspond to the peaks. Okay. So I'm going to just modify this, and I'll make sure it is taking all the peaks. So I'll keep it this point at this point. Then I think it has taken most of the peaks. So I will say, okay, this is fine with me. So you can play with this. You can increase this to 50, 100, okay, and then you can drag this, and you can also change the sensitivity to make sure like all the peaks are identified. Okay, so once you can see here, once it is identified, it will it will put a line in this place. Okay, so this lines corresponds to the peak position. Okay, so then you can say okay, fine. So now I have done the peak search. So I have taken all the peaks. So if you want to do now search match, you can directly click here, or you can do it restraints. Okay, so restraints, if I know what are the elements which are present in this sample, then I can do restraints. If I don't know, let us assume I don't know anything, then I will just click this search match. Okay, so if I do this search match, then it will run for slightly longer time, because it will try to find, or it is trying to index all the uh, possible things. Okay, so you can see the time taken by the software. In the previous case, when we did CO2, with the restraints, it took less time. But now with without restraints, without constraint, it is taking more time. Okay. So now you can see it is already put. It has given some examples. Okay. If I go here, PBS, so then you need to check the intensity ratio. Okay. So in this case, if you see, this intensity ratio is not good. Okay. If I take lead sulfate, okay, then if I take PbSO4, then what happens? You can see the intensity ratio would be same. Okay, that is the reason I took this example. So if you take here, in this case, this intensity is 28, 24, 820 and around 700. Okay, 520 around 470. So these intensities are almost same. But if I take the same PPS, you can see the peak position is shifted. So this second line corresponds to PPS. Okay. So you can see the peak position is shifted, and it is, even the intensity is not matching exactly. So in this case, you can see 800 is okay. But in the first peak, when you see, there is a mismatch in the intensity. So if you keep seeing properly, then you can see here, you can see this is 200, but your database is giving 320. So if you take this main peak and the next peak, this intensity is not good. So you cannot take this is a PBS. Okay, it should be PBSO4. So if you take the PBSO4, you can see the peak position is shifted to the same, to the original position, and also intensity is going to match with the with your data. Okay, so this, then if you want to know, or if you want to select this is my phase, then you just click here. Okay, so then it will go to the next one. So let us I will just try to take only the PBSO4. Okay, and if I want to know what is the space group, then I just go here, click on the card, show card. Then if I click that, then what happens? It will give, okay, so this is orthorhombic uh, crystal with the PBNM space group, and A is equal to 6.95, B is equal to 8.48, and then C is equal to 5.39. Okay, so then it will also give some calculated cell volume and all those things. So this is how you can actually do the your phase matching. Okay, so you can what we'll do is we'll just try to do this. So now if you take PBSO4 like your and then you will see the data for your PBS. Okay, so now if I go to PBS, so as it was showing similar peaks, and if you see here, it is having the same symmetry, but it's slightly different, PP and MA. And then even if you see the ABC parameters, they are very close to the one before. Okay, that means these two are having the similar symmetry, but they are different. They are quite different. Each one is quite different. Okay, so this is one way to do the, or this is how you do the phase matching. Okay, so this would give the preliminary information about your sample, like your space group and ABC parameters. This data you can use it for doing your profile fitting and retool refinement. Okay, and also you know whether it is a pure phase or mixed phase or impurity and those things. Okay, so with this, what I will do is I will try to show one for multi-phase. Okay, so if it is having two phases, like for example, in case of your uh, SiO2 and NaCl, if it is not reacting, that means you have two different phases. So we will try to do one example for that. Then we will going to take a break. Okay, so you can. So what I will do, I'll go here, and then I will try to import some mixed phase. So just a minute, because there are too many files. So Okay, so I am going to take this some unknown sample. So now what we'll do is we'll try to see whether it is a pure phase or mixed phase or whatever it is. Okay, so now first step is same thing. You go to pattern, go to background. So here you can see it is putting some points on the middle. So I want to remove that. I am going to click this. Then I click the right click here. So I'm going to remove those things because that is not the background. It is it belongs to some peaks. Okay, so if I want to go to the right, I can go to right by using this. So I will see the pattern. If I have any other extra peaks or extra points, I will do that. Okay, so now if I'm happy with then I'm going to say it is okay. Next I'm going to again do the peak search. Okay, so now I will do the peak search. So if you can see here, it is putting too many peaks in the but there is no peaks here. So for that, what I do, I will increase this to 50 and I will try to drag it. Okay, so you can see now, so try to uh, put all the peaks. If not, we'll do it manually. Okay, so now what I will do is I'll remove all these things because I don't want all this peaks. This is not exactly a peak, so I'm going to remove this. Then if I want to insert, I'll just click the left button. Okay, right button is to remove and then left button is to insert. So I will go to the next part. So this, so I can add these peaks. So the second peak is normally from your K alpha. Okay, so anything above 50, if you start seeing two peaks, here also this will be due to K alpha. Okay, so when you take the peaks, try to pick the peak in the center of the peak. Okay, not like the highest peak, not the in the middle. Okay, so something like this you have to take. Then we will do the I think this is sufficient because we have taken most of the peaks. So now let us do the phase matching. So as I don't know what are the phases, so I will just do search match. If not, I can give the restraint. Okay, I will do search match, then allow the software to find what are the possible phases. Okay, so now you can see here. So if I just zoom this portion, uh, you can see the black lines corresponds to the exponential peaks and green one corresponds to CR2O3. So the first phase is CR2O3. So if you see, it is not taking in all the peaks, but it is taking in only few peaks. So let me take this is one of my peaks. Then what it will do, it will go for the second possible phase. Okay. So now you can see there are instead of two, it is three. First one is peak from your exponential data. Second one is from your CR2O3, which is in yellow, and then green is from the next phase, which is the calcium carbonate. Okay, so now you can take, okay, so you can see uh, the first one took some peaks, the second one is taking some other peaks, but it's not taking all the peaks, but it's taking only few peaks. So now let me just consider this is my second phase. Then what it will do, it will try to put the next phase. Okay, so if you see here now, it has taken calcium fluoride as one
Sounds
more
okay.
phase. Okay, so now if I click this, then it will go to the next one, but your next one is the same like your previous one. Okay, so what you are supposed to do is you should see each peak is whether each peak is corresponding to some phase. Okay, so the first peak is corresponding to the second phase, then the second peak is corresponding to the first phase. Okay, so then this peak is corresponding to the third phase. So you can see all the peaks are having some corresponding database phase. Okay, so this is actually mixture of three phases. So if you have three different phases in a given sample, or maybe two phases, then this is how you can do the matching. Okay, so again you need to take care about the peak position and the intensity ratios. Okay, so those things you have to take care. So if you see here, This is 340, 320 good. Sorry, 130, 120 good. This is 190, 180, it is good. 160, 170. So these peaks, peak intensity are almost okay. Okay. So this is how you need to take care about the multi-phases. If you have multi-phase, this is how you do the multi-phase. Okay. So what you are what you can do is this will be given as one of the assignments. So tomorrow you have to do this kind of phase analysis, okay, or phase identification. Then you need to give the information, okay. So what are the information you're supposed to give is you go click here on the chromium oxide, then you open the card, then you have to give this information, okay. What is the space group for chromium oxide? What is the A parameter, B parameter, C parameter, okay. All this, and then volume. What are the volume? So this part you have to give in your assignment, okay. So this is what you have to do. Then you should you can see here it is giving some quantification. This may not be exactly 100% quantification, but it is a good starting, okay. So if you see here, this is like 15.2%. So in this sample, chromium oxide is 15.2%. Then calcium carbonate is around 28%, and the calcium fluoride is around 57%. Okay, this is very rough estimate. How to get to very reliable is when you do the retool refinement. Okay, so we are going to take the same example and we'll try to do retool refinement later in the workshop, and we should get this kind of quantification. Quantification means what is the weight percent of each phase. Okay, so these things we'll do again. So I think if this is clear, we'll stop at this point. And okay, I will take this question, then we can start. Can two samples with different concentration have same pattern? And if yes, how to differentiate it using XRD? So if you are having two different constitution, that means you are having two different elements. So the intensity of the peak corresponds to the element which is present. Okay. For example, if I take cerium oxide will have better diffraction, less absorption. Okay. And if I take lead in case of cerium, then what happens? Lead will absorb more and it will have less reflection. So the intensity will be reducing. So this is how you can even if there two samples are having the same pattern, their intensity will be different. It won't be same. Okay. So this is what we saw even in case of PbSO4 and PbS. PbS and PbSO4, they have almost similar X-ray patterns, but if you take the intensity rate, it won't be same. Okay, so that is how you can actually do the you can actually get the phase analysis. Okay, or you can distinguish two different patterns from two different constitution. Okay. Okay, after removing some peaks, can the data be used in the ripple refinement? See, all these softwares what we are using, so whether we are using Foolproof or QualX, they won't change your data file. They will not change the original data file. Data file will be remaining same. Okay, even if I'm removing this peak here, it doesn't change the data file. Data file will be you cannot touch those data files. Okay, so those data files will be as such. Only the calculated file will be generated. It will be a new file, not like it is not going to overwrite your data file. So you don't worry about playing with this, because you will never change you will not make any kind of changes to your original data. Okay, so original data will remain as such, so it will not change. When we comparing the intensity, the peak which has maximum intensity only need to compare or more peaks. See, always try, you need to compare at least 6-7 peaks. More, it is better to compare the intensity peaks, high intense peaks. For example, in this case, you need to compare this peak, and then these peaks which are having more intensity, rather than comparing the small peaks. Okay, so these small peaks may not give very good statistics, but better try to compare uh, high intensity peaks. So as this is a mixture, it is not a good example. But if I take some other simple example, for like your CO2. So in that case, what happens? You can compare the intensity of 1, 2, 3, 4, maybe one of this. Okay, 5. You don't have to worry about the very small peaks. So try to match for at least 5, 6 peaks. So that will already give you the complete information. Okay, so minimum 5 to 6 peaks is sufficient for comparing intensity and also the position. If this peak position is changing, then that means it's not a good phase. Okay, so this is what you can do. Okay, so I think we'll stop at this point and then we'll continue in the around 11:30. So then we will go to the profile fitting. Okay, so you have to join using a different link. I think